Okay, so here we are looking at a quadratic function, like parabola, like opening downward, with two lines. One line is passing through, like intersecting the function twice, and the green line is just grazing the function, the quadratic function, only intercepting the function once. We call this blue line a secant line, and we call the green line a tangent line. Now, we want to investigate two types of rate of change here. We want to investigate average rate of change, which I will abbreviate as AROC, average rate of change. Okay, average rate of change is simply rise over run that you learn in Algebra 1. It's just slope of that secant line, the blue line, which is rise over run, or delta y over delta x. The average rate of change, what's changing? Y, the y coordinate has changed from 3.5 to 8. And the x coordinate has changed from 1 to 4. So the y coordinate changed from 3.5 to 8. That's a change of 4.5 increase. And x increased by 3. So that comes to an average rate of change of 1.5, meaning every increase of the x-coordinate by 1 unit corresponds to an increase in the y-coordinate by 1.5 units. Average rate of change, the rate of y relative to x, 1.5. Now, calculus is more interested in the rate of change at the instant when x equals 1. This is the average rate of change, on the interval from 1 to 4. From 1 to 4, the average rate of change on that interval is 1.5. But calculus is interested in the instantaneous rate of change. And that is the slope of the tangent line. How fast, what is the rate at which the y-coordinate is changing relative to the x-coordinate at this instant? Well, we can approximate the instantaneous rate of change using the average rate of change. Now, this average rate of change of 1.5 is probably not a very good approximation of the instantaneous rate of change at x equals 1. However, if we take the average rate of change on the interval from 1 to 3, that will be a better approximation, because the slope of the secant line, the blue secant line, is closer to the slope of the green tangent line. If we take if we figure out the average rate of change on the interval from 1 to 2, that's an even better approximation. The interval from 1 to 1.5, average rate of change, would give us an even better approximation. Basically, the point is we can approximate the instantaneous rate of change, the slope of the green line, by calculating the slope of the blue line over shorter and shorter intervals. That's the idea behind differential calculus. So in order to do this, we want to first, I'm not going to be able to evaluate the function very easily. I can tell from this cool demo, this cool GeoGebra thing, what what the y coordinate of the function is at 3. It's 7.5. And what it is at 2, looks like it's exactly 6 when x equals 2. But when I get down here, it's going to be more difficult to calculate that average rate of change. It's going to be difficult to find the y coordinate of the red point. So what I'm going to do is I'm going to set the calculator up to do this for me. But in order to do that, we need to know what this function actually is. So we know that the function it's a quadratic function and it has 2 zeros. So we know it's going to be something along the form of it's going to have factors of 8 and x minus 8. And we know that the vertex is at 4, 8. So the y coordinate is 8 when the x coordinate is 4. So 4 times 4 minus 8, that's negative 16a equals 8, which tells us that the a is negative 1/2, which tells us that this function is negative 1/2 x times x minus 8. That's the equation of that quadratic function. So let's put that in a calculator, and I already did that. In y1 we have the function. Now, what I'm going to do is I'm going to set a table up so that the y coordinate, of the function is input into the table using by just inputting the x coordinate I put in. So I'll explain what I mean there. So the statistics key and then the enter key will get us into our list menu, into our table where we can enter. So we are interested in the y coordinate at, well, let's start with, let me go back to the here. So we're interested in the y coordinate at, well, let's start at 2. Well, we can tell it's 2 at 6. So let's start at, we want to know what the y coordinate actually is at 1.5. It's somewhere in the vicinity of 5, it looks like. So 1.5, not 1.2, 1.5. Okay, and then let's bring it in a little bit closer. Let's see what the y coordinate of the quadratic function is at 1.1. I can zoom in and get a decent, but 1.1. Well, let's go even closer. Let's go to 1.01. And we have to enter all of these desired inputs beforehand, because now I'll go one more. Why the heck not? The calculator will do it. All right, now let's go over to the second column and define L2 as the y coordinate of that quadratic function based on the input in L1, in the L1 list. So I'm going to define this as alpha trace y1 of the L1 value. Okay, so here we have the y1 of the L1 value. Now, in L3, what I want to do is find the, let me zoom back out some. So L3, I'm going to put the rise I started with 1.5. So looks like in the vicinity 4.88. Okay, 4.875. But I want the rise. I want the calculator to calculate for me this rise from 3.5 up to 4.875. So I'm going to define that as the difference, the 4.88, which is the L2 value, minus, well, let's plug in the, it's 3.5. The y coordinate of the when the input is 1 is 3.5. So L2 minus 3.5. Now notice what's happening to these rise values. The change in y, well, it was a 13.375, 0.295. It's getting smaller and smaller and smaller. Okay. In column 4, I want the run from but the difference between the two inputs. So from 1 to 1.5, for example. Oops. From 1 to 1.5, it's going to be a 0.5 run. This will be a 0.1 run, a 0.01 run, and so forth. But, okay, so we're going to define L4 as the L1 value, which has the x-coordinate of the red point, minus 1, which is the x-coordinate of the point we're trying to find the instantaneous rate of change, or approximate instantaneous rate of change. And now in L5, we're going to find the average rate of change between the blue point and the red point. So the L3 column has the rise in it, and the L4 column has the run in it. So L5 will be the rise L4 divided by L3. And I immediately recognized that I must have made a mistake there. Even experienced math teachers, let's see, rise divided by run is L3 divided by L4, not the other way around. We were calculating the reciprocal of the slope. So L3 divided by L4 will give us. And even this 3 isn't actually 3, it's 2.9995, 2.9995, 2.995. So 2.99995, if we backed up to 1.0000001, it will be 2.9999995. So, we're getting better and better approximations of the slope of the green line by taking the slope of the blue line at smaller and smaller intervals. And so, what would you guess, this is the calculus question, what would you guess the actual slope of the green line is? I'm not going to answer that question because I think it's fairly obvious.